Welcome to our technology series, part of our corporate Bytes collection of podcasts that we're doing. And I'm Rich Bowers. I'm the AVP of our Cognition Jump program. And today, to kick off this series, we thought we'd talk a little bit about machine learning. And for those of you who have maybe been through our program or interact with any of our trainers, I brought in our version of the expert, potentially the industry version of the expert. Jamison is with us, and he's came through the program and talked about machine learning from the initial stages. I think he even brought up maybe during our town hall conversation, one-on-ones we've had before. And so welcome, Jamison. Looking forward to chatting with you about machine learning today. And then we also brought in our technical manager, our trainer of our, our manager of our whole training program, Matthew Truelove. So, gentlemen, thanks for joining me today.
Thanks, Rich. Great to be here.
It's fantastic to be here. Very excited. Thanks.
Wonderful. All right. Well, let's dive into it. Why we are here, right? We are here to learn about machine learning. It's a very interesting topic, one that you hear about all the time. I mean, I think it's on commercials now. It's talked about in movies. A lot come to mind. So to kind of separate, fact and fiction, or fiction from fact, I should say. Jamison, what is machine learning? Like if I was a 5-year-old and in basically the situation of the depths of technology, I feel like one. What is machine learning? How would you explain it?
If I was going to explain it to a 5-year-old, I'd probably I'd use something like a toy robot, for example. You got a cool magic little toy robot that can sort blocks by color. But at first, it doesn't actually know how to sort blocks. You actually have to teach it. That's part of it being a toy. You basically show it a block, and you tell it what color it is. Then you put it down, and you show it another block. You tell it what color it is, and you put it down. And then you let it try. And at first, it's going to make a whole bunch of mistakes, of course. But you correct those mistakes. And by the end of the process, it knows how to sort blocks by color. And that's sort of what machine learning does, except instead of blocks, you have much more complicated things like pictures and words that have a lot more things going on with them.
Okay, yeah, and I can imagine. I mean, we don't just hear about the blocks being sorted, but I have a question for you. When you say, when they sort the blocks by color, you're obviously programming it, teaching it what color is, and maybe we'll dive into that a little bit more. But how about the corrections? Like, how do you go about correcting them, maybe putting a different shape into that pile, or maybe a color that may be bluish green as opposed to just blue? Like, how do you make those corrections on the back end?
Gotcha. So often depends on what kind of machine learning you're using, but in general, you go through training and testing phases. So you have the training phase where you are feeding it data and it is learning on that data. And then you are testing it based on new data that's not part of that original data set. And based on how it does on that, you assign it a score. And the model's main goal is to bring that score as low as possible, since it's a sort of a gulf way of doing things. It's called loss, the score value. And so the robot's goal is to bring that loss down as much as it possibly can. And theoretically, that's supposed to make it much more efficient at the task as well, based on how you design that loss metric.
Okay, that's interesting. Actually, I never even heard about a loss score. Matt, are you familiar with that at all?
Not as familiar as with loss. Does that have anything to do with bias at all, Jamison?
I would say bias more applies to a particular data set. Certain models can, of course, be biased based on their data sets, but when it comes to bias, that's sort of more of, let's see. Well, there's a lot of ways to measure bias, but you're usually doing it through the data set. You can also evaluate specific models to try and eliminate bias based on a bunch of different statistics-based stuff. And of course, all the data set stuff is statistics, but that tends to be where most of making a data set and making it high quality, most of the effort goes. Those data sciences are trying to use as many statistical methods as possible to ensure that that data set isn't biased in any way or discriminatory in any way. But when it comes to loss is sort of more of just a way to gauge the efficiency of a model that you're training while you're training the model. It starts off pretty high, so you have a pretty high loss rate, but the more stuff that the model tries during the testing phase, the more it's going to learn and the less loss that you're going to have throughout the training phase, if that makes sense.
Okay, so you're doing a little bit of it's a trial and error, right? With data kind of plugging and playing. So kind of I wanted to ask this a little bit later, but I feel like we're right there, and just to get a full grasp of it, right? So we initially program, right, or share various data sets with this robot or machine or application, right? I guess would keep the umbrella of it all. And what they'll be able to do is they'll pull maybe repetitions or things that they've noticed patterns of within that data set, and that will teach it that whatever it's doing is correct based on the data set, right? And then as it practices, just like anybody who's trying something out for the first time, people will give it adjustments. We'll make adjustments by maybe removing things in the data set that might have caused bias or it going in the wrong direction, and add things that might make it more, I guess, accurate or clear. Is that a nice synopsis?
Yeah, I would say so. Like you're finding out specific features that may affect the model in certain ways, in greater ways than others, and you're sort of focusing on those particular features as you're training the model. So let's see, what's a good example? I would say maybe housing prices over time. If you have data of, say, just average house price in a specific state for each year since, say, the 90s. You can actually use that data and use machine learning to make a prediction on what the price might be later on in the future. And it's still implementing loss in this regard. It's basically trying a bunch of different numbers at first, and then the closer it gets, or the lower the loss gets, the more it knows which things to focus on, basically. So when it comes to simple examples such as the house pricing, it's really just focusing on that one thing, price. But when you put in a whole bunch of other variables, like machine learning tends to do, you have to figure out what to focus on, right? And so that's where a lot of designing models comes into play.
Okay, cool. Yeah, super interesting. Matt, did you want to add in to that?
Yeah, Jamison, when you're talking about like predictive evaluation of housing prices and that sort of stuff, that makes me start to think of kind of some definitions and actual application, really with AI, right, with artificial intelligence. And I struggle, kind of distinguishing between the two. My understanding, machine learning and AI can go hand in hand, right? Very complementary with one another. But would you be able to kind of clarify each of those domains for us?
Of course, yeah. Thanks for bringing that up. That's a really important thing to distinguish at first. So AI is sort of this big umbrella term, artificial intelligence, and it's in general, the definition is any man-made object that performs a function which requires intelligence. So that's like a lot of things. That's pretty much most tasks that humans perform, right? But we have replaced a lot of those tasks with AI. Like you can, with this definition, you can count a calculator as an artificial intelligence. So they've been among us for decades.
My Zumba is artificial intelligence as well.
Oh yeah, definitely.
Right. All right.
For
Watch
sure.
out for that thing.
Whereas, let's see, machine learning is sort of a subset of AI, not sort of, it is. And it developed after the concept of, or the field of artificial intelligence was starting to really get going, I think in the 60s or so. Machine learning started really getting going probably like a decade and a half after that. And it was focusing specifically on statistical aspects, like generating data sets and training models that use those data sets. So specifically focusing on database models as opposed to using formal rules that a lot of other AI can do. So like a calculator understands math because it's been programmed with these formal rules. It hasn't actually been taught that math. It just has it in its code. Whereas machine learning, specifically, you start with a model that's designed for a specific task, but it hasn't been trained to do that yet. And then you give it data that will train it, and then you test it, and you repeat until you have something that you're satisfied with.
Okay, and forgive me if this is a silly question, but so AI, the umbrella term, right? And then you have other things we may get into, deep learning and NLP with machine learning. Does AI, you mentioned it's kind of just in its code, correct? I think that's what you just shared?
Yep.
And so does that mean that, does it use machine learning as well, or is that just a whole nother potentially podcast for us to dive into?
Not all AI uses machine learning. So back to the calculator example,
Yeah.
that's not machine learning. But you can, I think at this point for sure, you can teach a model math with machine learning. So it's sort of two different methods of achieving the same thing. You're getting a computer to perform a task, but one way is coding out a little brain for them to learn with. The other is making that brain and giving it knowledge already.
Okay.
Very cool. I kind of want to tie back then to Rich's point about the Roomba on top of the clarification you provided here, Jamison. So when the Roomba, the little robot vacuum, right? When it goes around your house, oftentimes when you first turn it on, it's kind of sensing where the barriers are, the walls, the couch, all that sort of stuff. And I believe the idea is on subsequent runs over the days and weeks that you continue to use it, it is faster because it's mapping out where everything is. Would that be kind of AI using machine learning?
Definitely, yeah. So exactly, the Zumba is basically mapping out your entire house, and that itself isn't necessarily machine learning, but the actual pathfinding portion, like making it like know where to go, having it have that own decision making process, that's definitely machine learning. So it would map things out, and then based on trial and error, it would figure out the fastest route to make your house as clean as possible.
Excellent. And critical follow-up question, is it Roomba or Zumba? I think we've all said
I don't know.
I think one of those might be a dance.
It is.
Right?
I can't tell the difference. I'm
So,
sorry, I don't have either.
No, I don't. I'm not sure actually at this moment. I think Matt, I'm going to go with as the married individual in this, keeping the house clean, and everything. Is it Roomba?
Yeah, having 3 dogs, it is definitely Roomba, and I'm very familiar with them.
Well, excellent. Jameson and I, we show up for a Zumba class. So okay, and then so there's a lot of uses. It seems like of machine learning, and I don't even know where to start, and that's why I'm glad you're here. What do you think are some of the main reasons why we're so interested in machine learning, and not from a pop culture standpoint? I'm probably gonna ask that later, but from an actual use case scenario, what do you think some of the main reasons are?
Yeah, I mean, at this point, especially with the speed at which it's progressing, machine learning is pretty ubiquitous in almost every industry. You can find applications of machine learning for sure. Let's see, what are some good examples? So first off, image and speech recognition, of course. So identifying objects in pictures or transcribing spoken words into text. So you have your face recognition on your phones. It's been out for a while now. That was a nifty new thing when it came out. That you don't have to put in a password. You can just have it look at your face and it knows it's you. And there's Google's speech to text engine, which I'm sure a good portion of people have used at this point if they've used Google before. Let's see, what are some other applications? There's predictive analytics, so using historical data to make predictions about future events, such as the weather or stock prices or housing prices or customer behavior. That's used very, very often in a whole bunch of different industries. Probably one of the more simple applications of machine learning, but still very, very useful. Natural language processing is a big one. So with natural language processing, models can understand and generate human language, such as for language translation or sentiment analysis. So you're able to have a model that is understands, or a bilingual model, sort of, as opposed to having to walk around with somebody who is bilingual to be able to translate things, or a little book. That's definitely not as efficient. Let's see, robots and autonomous systems are always using machine learning, of course. So we can control and navigate robots, and for say cars as well. So example would be self-driving cars, of course. That's a big thing as of this moment. Let's see, something more safety-wise, there's fraud detection. So we use machine learning to identify suspicious patterns in financial transactions and detect potential fraud that way. Do the same thing with malware or viruses on your computer. See if you can find traces of viruses based on previous data. In healthcare, you have medical imaging. You can make a classifier to find tumors in medical images or MRIs. You can do drug discovery. You can use machine learning to create new drugs, and personalized medicine, which is, I hope, going to be more of a thing in the future, where you have these drugs or these treatments designed specifically for you, with all of the data that comprises you in mind, which I'm particularly excited for. That's something that I'm hoping definitely takes off in the future.
Yeah, that was great, Jamison. Oh my gosh, there's a lot of use cases, and I believe there's even more. I know Matt's probably biting at the bit to probably get in on that, though. Matt, did you want to chime in?
Yeah, for the benefits of our audience here who are totally seeing my face right now during this audio podcast, I'm very excited to check in with Jameson on a lot of those examples brought up. You talk about like drug discovery, self-driving cars. I think most people who are familiar with the topic, superficially at least, with machine learning, have also probably heard the idea of deep learning, right? Deep learning. Anything, well, first of all, what is deep learning? And out of the examples you gave us, is there anything that could fall in that category?
For sure, definitely. Let's see. So a good portion of image and speech recognition is definitely deep learning. I would say most of what I was talking about, you can actually use deep learning for at this point. And deep learning is sort of an extension to machine learning, where machine learning is a subset of artificial intelligence. Deep learning is a subset of machine learning. So everything that derives from deep learning is biologically based. It's based on a neural network. That's what it's called, and that's basically just at its simplest. It's just a whole bunch of small little units that will take input, modify it, and then send output to other units. And when it comes to neural nets, these are stacked in layers. And so deep learning is based off of neurobiology in that regard. Whereas other subsets of machine learning aren't actually using that kind of neuron layer, or simplified version of neuron layer model.
And I think a general question overall is there, all of this takes so much data. Is it vast amounts of data, like unthinkable amounts at times?
Huge. Yeah, you can't even imagine it.
Where is it coming from? Well, like where's this data? Like, where are they pulling it from? Is it like the internet, and all of a sudden we're going to have an Age of Ultron type of situation on our hands, or where is it all coming from?
Yeah, that's a great question. So earlier on, before the internet, a lot of data sets, especially for natural language processing, were based off of corpora. And a corpus is just a really, really large body of text that contains a bunch of different snippets and examples that pertain to whatever data set you're trying to make. And these corpora can be huge. I can't even come up with a number at this point. I would say billions, if not trillions of words, honestly, with the corpora that we're doing now, probably more. But it is a lot of data for sure, and it takes a lot to manage and maintain it.
And sorry, just to follow up, I know Matt I know he loves this stuff too, but real quick, the data that they're getting. So I realize it's, a lot and a massive amount. For myself that haven't really studied this, like where's the accumulation of it from though? Is it just research papers? Is it stuff they have stored on computers over the course of years? Like, where does it, I guess, where's the original point, the origin?
Yeah, that's hard to say at this point. I would say most corpora are pretty extensively sourced. So that's actually part of the data itself is where it comes from, and that's usually at least one person's entire job when it comes to making this kind of stuff and designing it, because that's really important, being able to verify the credibility of your data. But at this point, most of it comes from the internet, or most of it comes through the internet, I would say, at least. So a lot of this kind of stuff is pre-verified on the internet, and we can stand on the shoulders of giants per se to create data sets that are sort of combinations of older ones, but may have more modern modifications, and maybe sort of agglomerated into one large data set.
Jamison, speaking of data origins, helping clarify AI versus ML, and our Zumba Roomba conversation, there's something else that I think of that comes to mind, and maybe not everyone's aware of this, but for those folks that watch professional American football, NFL, with Amazon Web Services, AWS, does something called Next Gen Stats. They have it in the commercials sometimes if you watch a game. And it does some cool stuff, including review of every play that happens, every down, and it's almost in real time where they'll take in. It seems like they'll take in data of the score, the time on the clock, the stakes at hand, the scenario, the players themselves, the play that was called, the defense. All that sort of stuff, past history, I think, of a particular play. I'm not sure if they get it, per team or for that play in general, if different teams run it. And they can do some really cool stuff, like talk about likelihood of making that catch, right? Or whatever it may be, or that play versus that defense happening. You see that in the sports world, I'm assuming, for fantasy football or betting applications. But do you see anything else taken in real time data to make those predictions? And my follow-up question is based on that scenario. Would that be supervised or unsupervised machine learning?
Gotcha. Yeah, that's a great question. And that's honestly one of my favorite applications of machine learning is being able to take that kind of live data and use it with an already trained model to give viewers and spectators, or even users, some really interesting insights onto that data. And especially when it comes to the more data, the better, of course. Especially with sports, we have some really great ways of capturing data. Like even in baseball, you have the camera able to detect the type of spin that the pitcher is giving. So that is absolutely fantastic. And using that data to determine a whole bunch of different outcomes and being able to display that to the viewers, we think that's definitely going to be part of the future of gaming for sure. And you see that in a lot of different places too. You see it, I think, with the self-driving cars. Of course, they have to take in real-time data and make predictions based on that kind of stuff. So you definitely see that as well. And when it comes to this amount of data, especially in this day and age, most of these models are actually going to use a mixture of supervised and unsupervised learning, because a lot of them are actually combinations of older models that may have used supervised or unsupervised learning. So when it comes to deep learning, a lot of it is unsupervised. It's mostly unsupervised, but it's based off of data that was made by supervised models. So you can, it's kind of a fuzzy area in this day and age, at least.
That's a no. That's a lot of cool information. So if I'm paraphrasing you a little bit here, Jameson, and breaking down the points, supervised learning facilitates unsupervised learning, and unsupervised learning is going to most often be deep learning. Is that fair?
Yeah, yeah. For when it comes to understanding, like having the model understand the data, at this point, it's mostly about designing the model based off of that data set. And that's where unsupervised learning comes in, and it facilitates the supervised learning models that way, because usually you're using unsupervised model or unsupervised learning models to get sort of a view or a grasp on the data set. It's more of like a statistical analysis kind of thing, and grouping, trying to find groups or trying to find patterns where you don't actually know if there are any. And that's why unsupervised models tend to use unlabeled data, or use exclusively unlabeled data. And you're trying to make those labels with the model. But then you can use those labels in other models. It's really just kind of a long train of models at this point.
So just for, again, just to get back into that. So unsupervised versus supervised. So it's not like, that does not mean that there's somebody behind the scenes watching them the whole time, right? It's not like that. It's not like, having a little kid running around unsupervised. There's more to it. I think you mentioned that's not labeled. Like, what is the difference in there?
Right. Yeah. So when it comes to supervised learning, that's using data that's already been labeled. So you already have given it an output that you want, and then you are giving the model all of that data as well as the outputs, and it's learning based on what you've given it, how to label future data that you give it. Whereas with unsupervised learning, you're giving it a whole bunch of data. It's probably completely unstructured, and you've barely looked at it. And you're saying, please find patterns for me. Please show me something that I haven't seen yet, so I can go somewhere with this.
Okay, that makes it way more clear than the way I was going through that. So thank you for it. So as we kind of get towards maybe potentially the tail end of our time, I know you have class and stuff. So as we talked about the main reasons for machine learning, and you listed a plethora of phenomenal areas that it can help on out. Are there any challenges that you see reoccurring? I know we talked about biasness previously, but any other challenges that could arise?
Oh yeah. I think machine learning is very much in not even an adolescent phase yet. It's still kind of structuring itself out. Reading like the literature on data science is still, I have experience with data science literature and normal science literature, more hard science literature, and it's just not as well structured. So the field itself is very much still growing, I would say, and there are a lot of different challenges that we face when it comes to making sure that we have good data quality, which is sourcing, having credible sources, having well-structured data as well. And that's where a lot of that work goes. Eliminating bias, as we were talking about previously, that's where another portion of that work goes. We focus a lot on overfitting. Overfitting can be a pretty big challenge for machine learning, and that includes training a model too well on a specific data set, so that it becomes perplexed if you give it new data and it doesn't know how to learn from that at all. So that's a big issue. Explainability. With some of the bigger models, it can be really difficult to actually interpret or understand what those models are trying to accomplish, especially deep learning models. And that can make explaining that model's decisions and actions difficult as well. And that's not what we want when it comes to data analysis. It's all about control theory and being able to knowing what you're doing when it comes to making something that can make decisions. It's kind of important.
Yeah, I mean, especially when you're talking about healthcare and safety, cars driving by themselves or robots. So
Right.
that all makes a lot of sense. So when you were talking about all of that and all those different challenges, I noticed you mentioned that we're probably not even in the infancy stage or adolescent stage, I believe is what you said. Do you feel like we're kind of behind where maybe, I think you mentioned AI started brainstorming, kicking around the 1960s, I believe, right? Is that what you mentioned?
Mhm. Mhm.
And then I believe there was a winter, an AI winter, I believe occurred where it kind of slowed on down. Why do you think, maybe it kind of gets hot for a little bit, maybe a summer, and then drops back down to kind of cold and not a lot of interest? Do you think that's just the way it is in culture, or is there another reason why you feel like we're behind and where we potentially could be?
I would say the most important aspect is going to be where the money comes from. To be completely honest, I mean, when it was shiny and new in the '60s and '70s, AI in general got a lot of funding from military companies like DARPA because they thought, oh, this is a game changer. We can definitely use this for a lot of things. And what the scientists were promising at the time ended up not being very fruitful. So DARPA stopped funding them. And that's actually where that AI winter came in. And a lot of it is public interest as well. If you have more AI in the public eye, then you'll have more funding on it, just because it's showcasing what it can do. But I would say it's a steadily growing thing for sure. It's always going to be increasing because interest for AI is always going to be increasing. But it's definitely about where the money comes from because making data sets is expensive and training models is expensive. And even just like having a model do something is expensive.
And so I guess to piggyback on it, is it that we're certainly more efficient, hopefully, than we were in the 60s, 70s, and 80s. And so now industries, like as you mentioned, healthcare and automotive or self-driving with Google and AI, excuse me, and Elon Musk's company over there.
Mhm.
In that type of situation, is it that the data sets have become more efficient and cheaper to do, and now the mainstream industries are saying, as opposed to just the military, right, are saying, "Hey, look, it's actually cost effective now, and that's why we're hearing more about it." Is that what your reasoning is?
I would say in that regard, it's honestly more likely because of the availability of the hardware. So we've made some really big strides, of course, since the '60s and '70s in terms of hardware, and training a model is very resource intensive. So we're actually different industries are investing in making specific intelligence processing units as opposed to say a central processing unit or a graphics processing unit. Um, we are making IPUs specifically to trade models. So there's a lot more investment coming from a lot of different industries that allows us to have the hardware to train larger data sets and make more complex predictions.
You said larger data sets too. That was just making me think, like compared to the 60s and 70s when there was the funding that you were talking about. What is one thing we have now? Big data, right? Memory's gotten significantly cheaper than it was, right? SQL was very efficient at storing data without redundancy and wasting memory because memory was expensive in the 70s. We still use SQL for speed and other reasons, but memory's cheap, right? So we can
Mhm.
have these large data sets. How does that factor in?
Well, memory is still the cap, honestly, when it comes to these large data sets. You are still limited by the amount of things that the program or the computer can look at once. So the higher the memory, always the better. But we have definitely made great strides since then, and the data sets themselves have been augmented to become so large that we can do some pretty crazy things with them.
So we're kind of coming up to time, and that little piece of discussion that we just had there. What I found interesting, among a lot of things during chatting with you today, Jameson, was it almost seemed like a discussion on business and technology, a true blend of that. Now, of course, unless Matt has anything else to ask or Jameson, you want to share some, my last question for you is: there's a lot of programmers out there, a lot of people who are interested more on the tech side, probably listening to this conversation. If you're looking to go into a career path of machine learning, or even just spend more time in it, when you're is there a priority on the programming, but there's also a priority on the business knowledge associated with it? How is that blend? And I know I'm asking you to predict the future a little bit, but do you see that becoming more intertwined in the future? What are your thoughts?
Yeah, honestly, I would say that the more that business embraces that kind of technology, the more that they're going to benefit from it, for sure. But when it comes to like an actual developer or programmer or a data engineer, even, I would say you definitely need a lot of Python knowledge and a lot of statistics knowledge, for sure. And that comes with learning how to use it. But it's definitely still important to know what the client or the shareholder is looking for and to stay on track to deliver a viable and satisfactory product. So ML scientists tend to focus on design and implementation. So responding to feedback from clients and shareholders and product analysts is definitely part of the job. But there's a lot of technical knowledge to learn too, and it takes a long time, but it's very much worth it, because in the end, from the way that I see it, you're making brains, and that's cool.
This is the future that we're talking about right here. This is the now and the future, right?
So. Yeah, I think so. Writing was basically replacing biological memory. This is basically replacing biological intelligence, and that's definitely going to be crazy in the long term.
That's amazing, man. All right, so we'll have to bring you back in 6 months. There'll be an update. Probably 3 months.
For sure. Anytime at all.
Cool, my friend. Well, I appreciate you. Your knowledge. I know this wasn't something that you studied overnight, but a passion for over years. And that's invaluable that you get a chance to share it with us. And so thank you for your time, Matt. Always love hanging out with you, my friend, and I appreciate your inputs too. But that's it for us on our end. And next time around, we might have Charles Dunn potentially join us. So who knows what topic that will be. I'll keep you all posted. But that's it for our technology series today. Thank you, gentlemen. See you later.
Thank you both.
Awesome. Thank you.
Bye, guys.